Look at properties of the root locus. In the previous lecture, we discussed and defined root locus, and next we are going to look at the properties of the root locus. Okay, so without computer to factorize the polynomial, okay, for several values of k, then it is not easy task. It's going to be very tedious for you to be changing the values of k and factorizing to find the roots of the characteristic equation after every change of k. Okay, therefore it is not very advisable for you to be doing that. Okay. But if we know the properties of the root locus, then we will be able to, or it will enable us to sketch the root locus without factorizing the characteristic equation. And then by being able to sketch it, it will give us some qualitative idea about how the roots behave as the value of k is changing. And with that, we might even proceed to be able to determine some specific values on the root locus that will help us to actually calibrate and know specifically how the system behaves by just plotting the root locus with those critical points. Okay. So the properties of the root locus are very, very important then for us to be able to know the performance of, or the general performance of a control system. So in order to discuss the properties of the root locus, let's start from what we discussed earlier that day. Overall transfer function of a closed loop system is given by k times g of s over 1 plus k g of s, okay, h of s. Okay, so with this, we know that the poles exist at values of s for which, okay, values of s for which 1 plus kg of s h of s equals 0. So if that is true, then we can say that kg of s h of s equals minus 1. Okay, any value of s that we plug into this, that we get minus 1, then it's going to be a root of the system. Okay, so if you plot any value, if you plug any value into this and you don't get minus 1, then it means it is not on the root locus. It is not a root of the system. Okay, so if this is the case, then what can we say about this? It means that k g of s h of s is equal to, now let's plot 1, okay, minus 1 here. If you plot it, if you plot minus 1 as a vector, okay, plot minus 1 as a vector, then the magnitude is going to be 1. Okay, so the magnitude of minus 1 equals 1, and the angle is going to be 180. So the angle minus 1 equals 180 degrees. Okay, of course, if you add 360 to it, so that will be 180 plus 360, and that will give you 520. And you know that 520 in terms of angle is the same as 180. So by adding 2 times 180 to it, we don't change anything. Therefore, it means we can generalize this as having an angle, so magnitude of 1, and an angle of 2k plus 1 times 180. Okay, degrees. So this is something that we can easily find from the characteristic equation. And where k equals, so this is small k, not a big k. Small k equals 0, plus minus 1, plus minus 2, and so on and so forth. Okay. So this is the knowledge we can find easily from this. And this implies that, okay, it implies that we have to make sure that the angle of this is always equal to 1, and then that can help us to find k. So let's interpret it. So interpretation of what we have just shown from the characteristic equation is that 1, any value s that gives, okay, the angle of KGH, okay, equals an odd multiple of 180 degrees is a pole of the T of S for a given value of K, big K, gain. Okay, so if you plug in any value and you get the angle to be an odd multiple of 180, then it means that that value of S is a pole at that value of K. And the value of K can be found from the same expression. So we said K, G of S, H of S equals -1. And I can find the magnitude of this, and that will give me K times the magnitude of G of S, H of S equals, okay, 1. And therefore my K equals 1 over the magnitude of G of S, H of S, which of course from what we have studied earlier is the same as 1 over the magnitude of G of S, the magnitude of H of S. Okay, so I can plug in the S and I'll use that to find out whether it lies on the root locus, and if it does, then I can use that value to find the gain at that particular value of S. Okay. Also note that since, okay, K is a scalar, okay, that implies that the angle of KGH is actually equal to the angle of GH. So the angle of G times H, which is the complex part, the complex number, is actually the same as the angle of G times H times K, because K does not contribute its real number, positive real number. It contributes 0 angle to the system. So putting it in more detail, what I'm saying is this, and this is very important, so I'm going to state it again. Okay, because this, we are going to use this actually for the root locus plot and then for the calibration of the root locus, and it is also going to help us to design parameters for a system in order to accomplish a particular performance characteristic, and then finally help us to design compensator. So this idea I'm going to share here, which is actually stemming from all the discussions we have had so far, is very important, and it's given that, so when we are given a point, okay, S, we can check whether it is a pole by evaluating the angle of the open loop transfer function okay, and the angle is going to be the summation of the angles of the poles, zeros, minus the summation of the angles of the poles, okay, and if we evaluate an if is an odd multiple of 180 degrees, then the point is a pole of the closed loop transfer function. No, note I didn't say it's a pole of the open loop transfer function. I said it's a pole of the closed loop transfer function. Okay. Otherwise, it is not a pole. Okay. And then if we discover that it's a pole, then we can find our gain, that is the value of k, which is given by k equals 1 over the magnitude of g of s times the magnitude of h of s, which we have discussed earlier. Okay. So I'm going to give you an assignment. And the assignment is that given the unity feedback system, so given a unity feedback system with the open loop transfer function g of s equals k into s plus 2 all over s squared plus 4s plus 3. You are to calculate the angle of g of minus 3 plus j0. Okay. B, you are to determine if the point minus 3 plus j0 lies on the root locus, and if it does lie on the root locus, then you are to determine the value of k at that point. I'm going to give you answers to guide you. Okay. For the A, the angle equals 180. Okay. Which implies is 1 times 180 implies it's a root locus, or it's on the root locus. Okay, and that is a pole of the closed loop transfer function. Okay, and then so that is B, and then your C, the answer k will be equal to 10. Okay, so you can go and do that, and that will end this section of the lecture. Next, we'll move to look at how to sketch the root locus using the knowledge we have learned and the properties of the root locus.